Okay. Welcome to EE123 Lecture 14. Woo! Sampling. Sampling is one of my favorite topics. Hey. Sampling is one of my favorite topics. I was just telling what is my favorite topic. Because it's where the continuous domain and the digital domain meet and transfer from one another, okay, which makes everything so much more interesting. Okay. So, announcements before we start. Ham exam. Okay. It's Thursday, 3/12. 7 to 10 plus p.m. At the WAS, Soda Hall. Remember that, okay? So it was a week and a half from now, or actually 2 weeks. 2 weeks from now. Okay. Lab. Who's having trouble? Everybody got it working? Okay. How about we do this? Who has not finished yet? Okay. Who has not even started yet? Who finished everything? Okay. The real time worked fine? Yeah? You saw airplanes? That's pretty cool. Yeah. Okay. So, Sunday morning, lots of airplanes. People arriving to San Francisco. Okay. What is this phenomena? I took it from YouTube. Yeah. So this is aliasing. And one of the reasons that you see this, is we'll see later, is because the way digital cameras today work, especially on small cameras, is that they, the way the shutter works is that it just turns on and off. And so you don't have this low-pass filtering of the blur if the shutter would be kept open. So although the black and white lines should have moved, they are kind of standing still because there's exactly the timing where the shutter turns on, exactly the same setup of black and white lines appear over and over again. And so it moves, but it turns off. And then when it turns on again, exactly the same setup. In that sense, frequencies that should have gone very, very fast are aliasing, or appears to be not changing, which means that they are aliasing to a DC frequency. Okay? So they're appearing as a certain frequency, but they're actually not. Okay, we'll get to this today. So the one thing, so today we're going to talk about sampling. How many of you have seen this before? Okay, all right. So next topic. Yeah, we're still going to go over it, though. And there is a reason, because every time you learn this, you learn a little bit more and in depth, and there's always these subtleties. Okay? So what is sampling? Sampling is really conversion from continuous time, which is continuous and non-quantized, into discrete time, which is usually quantized. So the number representation will be often quantized. A reconstruction is taking a discrete time signal, which is often quantized, and makes it into a continuous time, which is analog. Okay? Now, why do you want to do this? That's the reason you're here. Because there's a lot of stuff that you can do once you take the real world, you sample it, are able to represent it on a computer, do computation on it, and generate something, again, into the real world. Sometimes you don't need to generate something again. It stays in the digital world. And sometimes you do. Here's an example of something that was digitally produced, but now is displayed for you in the real world. Okay, this is analog. Okay? Although when you look closely, I can see the pixels. Okay? There's still, this is continuous time, right? There's no, although I can see the pixels, but they're continuous. Okay? And physically on this board. Okay? So there's a lot of reason to do this. Digital storage, for example, audio, images, videos, that's a classic one. Communication, any type of communication, whether it's fiber optics or cellular, there's a lot of processing that happens while converting into digital to analog and vice versa. If you want to do compression, correction, restoration, there's actually interesting work that's done at LBL when they scan old LPs and even old recordings, and they use image processing to actually extract the audio recording on those old devices that you really don't have a way to read them today, and then reproduce the music that they were recorded at, which is pretty cool. Digital synthesis, this is actually digital synthesis, what you see here, but you can also synthesize speech, you can synthesize images, you can use it for learning, so machine learning. You want to digitize things in the real world, learn from this, and decide on an action, classify objects, do operations, and so on and so forth. In order to talk about sampling, we again need to develop this language of how we describe these things, and this is what we're going to do right now. So, sampling of continuous time signals. Here's will be a typical system. Okay? You've got a signal, which we're going to call x sub c, which is the continuous version, and it's a function of time. It will go through some analog anti-aliasing filtering. Okay? So this is filtering in the analog domain, capacitors, inductors, MEMS devices, something that filters frequency in the analog domain. Okay? Then you've got the conversion, analog to digital conversion, okay, or A to D, ADC or A to D, in which there you have some device that makes samples. So at every time t equals n times t, so at intervals of capital T, you will get measurements of this continuous time signal. Okay? So now here it is discrete, but not quantized. Okay? Again, this is a model. Okay? So x of n will be the evaluation of x of c at time points n times t. Okay? N equals 0 would be at time 0. Then that will be the value there. N equals 1, that will be a time capital T, and so on and so forth. Then it goes through some quantization, which is bit representation, whether I have 16 bits, 14 bits, 8 bits. This device over here, for example, has 8 bits of accuracy. What about your A to D, like your microphone on the laptop? I think about 16 bits, because this is actually a good representation for audio. We'll talk about what does it actually mean to have that representation of quantization in terms of bits. What is the implication of having a representation of 8 bits compared to 16 bits? Yes, it's more accurate, but how are we going to model those errors if we don't? Okay. So after that, you've got quantized discrete samples, which we're going to do some discrete stuff on them. Okay, for example, store them, do some DSP, and so on and so forth, and we get y of n, which is a, again, discrete time signal. And then it will go through a digital to analog conversion, or D2A, and we'll reconstruct it to produce a continuous time signal y sub c. Okay, so this is the model that we're going to have. If you think of a camera, X of c could be a three-dimensional space, two-dimension in space, and one-dimension time, for example. That would be a camera. If you think about a 3D camera, that would be a four-dimensional space. If you think of a beautiful MRI machine, that could be four and even five-dimensional space, or even six, depending on what you do. Okay. So now let's talk about, in order to analyze what actually is going on, we're going to idealize things into an ideal model. And again, we're going to develop a language that would eventually allow us to understand what's going on when things become non-ideal. You'll see them today if I'm going to make it. So x sub c of t goes into, and this is the notation in the book, through a continuous to digital conversion. When we talk about this means that this is ideal. Okay? It does exactly what you want. That device here takes t as the sampling rate, so it's going to evaluate the function at this particular sampling rate. And then you're going to get x of n, where x of n will be equals to x sub c n times t. And we're not talking now about discretization. There's no quantization here. Okay. So if this is x sub c of t in red, the green is the evaluation of x of n at points equals t equals n times t. Okay. So this is discrete and continuous. Okay. Now, in order to get to here, what we're going to define a tool, which is just a model. Again, it's not something that is realistic, but we're going to define an impulsive function, or define impulsive sampling. So a new function, which is x sub s of t, which is really a series of shifted impulse functions, or delta functions, at intervals of capital T, in which the coefficients of these impulse functions are the evaluation of the continuous time function x sub c of t at those points. Okay? So instead of having this type of a model, where here I have n and t, and it looks like this, now I have two continuous functions, right? Delta function is a continuous function, so Dirac is a function of t. Okay? But is it impulsive? So we're going to use this as the model. So x sub s of t is basically just shifted impulse functions at intervals of capital T that their coefficients are the evaluation of the continuous function. Okay? This is not really sampling per se, but if you think about the coefficients of those delta functions are the samples. Okay? But this is still a continuous time function. Okay? So x of s of t is really the multiplication of x sub c, which is the continuous time function, with an impulse train. An impulse train with impulses, unit impulses, at intervals capital T. This is not really physical. What we're going to use this is we're going to use this for modeling and derivation. And you'll see what that leads to. Okay? So we're going to have an intermediate stage between x of n and x sub c that is going to be this x sub s. That's the tool. And so the question is really, what is x of n related to x of s in the frequency domain? Okay. So you can compute the continuous time Fourier transform of x of s. You can compute the discrete time Fourier transform of x of n and see how they relate to. So let's look at this. In the frequency domain, x of s is continuous time. So it is capital X sub s of j omega it's supposed to be an integral, right? But because when you integrate over delta functions, you basically just sum their coefficients because the area underneath the delta function is 1. Okay? So it is a sum of x sub c n times t and, of course, the Fourier kernel corresponding to the particular n. Okay? What about x of n? It is related to x of e to the j omega, where now we're summing over all those x of n's, and I think this is a mistake, so I apologize for this sub s. And you could have earned $1, but you didn't. Okay. It's x of e to the j omega of the sum of x of n e to the minus j omega n. So really, if you just look at these two functions, it's small omega equals to capital omega times t. Okay? So this is how this relates to the sampled version of it. Okay? So now we have a nice relationship between the two, okay, between x e to the j omega and x of s in the continuous domain, okay, where omega here equals to omega over t, or the other way around. So now let's think the other way. Okay, so we have a relationship between, it's actually pretty nice. All it says is that what I need to do is I can take the continuous time Fourier transform, and instead of putting capital omega, I need to put omega over t. Okay, that's what it says. What about the relationship between x sub s of t and x sub c of t? So the continuous time version and the impulsive function. It is really what we defined it as, right? This is in time domain is x of c multiplied by this delta train. Okay? So now we need to compute the Fourier transform of this. Okay? Just a notation break. Okay? This is a impulse train. Sometimes it is written as a Shaw function or an impulse function or a impulse train function, or what's the other name for it? Comb function. So if you just recall that a comb function of t is really the sum of delta that are shifted by an n, if you're actually shifting them by n times t, if you play around with what's the definition of a delta function, if you have a delta, a scale delta is really 1 over absolute value of the scaling multiplied by the delta. And you can actually show that very easily. But if you actually take this into account, then in the case where you are shifting by t minus n times t, if you want to write that in terms of a comb function, you need to scale it. Do 1 over capital T times the Shaw function or comb function t over capital T. This has still magnitude 1. Okay? And it's shifted by t. Okay? It's just by this scaling and shifting theorem of the Fourier transform that you've learned in 120. Okay. So now, how is it related? Well, if you've got S at t that leads to Sj omega, and so in this case, when you have so what's the Fourier transform of a comb function? It is a comb function. Okay? So if you remember, something that is impulsive in one domain is going to be periodic in the other domain. Okay? So what is something impulsive and periodic in one domain is also going to be impulsive and periodic in the other domain. So it is still an impulse train. So the Fourier transform is still an impulse train, only that the distance between the impulse function is now inversely proportional. Okay? If I had them close in the time domain, they're going to be further away in the frequency domain. So their scale at 2 pi over the time interval. Okay, you remember that? 120? Remember? Okay. So now I still have a impulse function in the frequency domain. So what is the multiplication in the time domain? How does that translates into the frequency domain? a convolution. So if I multiplied my signal in the time domain by an impulse train, it is corresponding to the convolution of the Fourier transform of my continuous time domain signal and the impulse train. Okay. So what I get effectively, if I convolve with this impulse train, okay, I get effectively a sum of shifted versions of my signal. Okay. So now I get replicas of my signal that are centered around each one of these impulses in the frequency domain. What is the distance between these impulses? 2 pi over capital T. Okay. If I'm lucky, those replicas are not going to be overlapping. In that case, I am preserving the information that I have in the original signal. If I'm not, then there is going to be some overlap and I might lose some information. Okay? So now if I have a signal S of t that I'm now going to, so now S of t, which is the impulse function, has a distance of sampling between of capital T. The Fourier transform of it is inversely proportional to 2 pi over t. So if I have x sub c of j omega, or capital omega, the continuous time Fourier transform, to be band limited between minus omega n and plus omega n, and if omega s, which is corresponding to 2 pi over t, if that is bigger than twice the bandwidth, then I'm not going to get any overlap. So if every shift is bigger than twice the bandwidth, then I'm not going to get any overlaps. Okay? So now I'm going to put my replica over this one, replica over this one, replica over this one. If the distance between them is enough so that they fit, then I don't going to get overlaps. I can say that once again, but I think that's not going to help. Any questions? Is that clear? Have you seen this before? Who has not seen this before? Okay. Okay, so what will be the case if that is not true? What if my sampling rate is below this rate, the rate that I need? So now what if my bandwidth was a little bit wider? What would happen then? If my bandwidth is wider, then each of the signals are going to be replicated, and the replicas are now going to be overlapping. And this is what's called aliasing. Okay? So take a look at this. You see this? This is a single replica. That's what I would get eventually. That will be corresponding to minus pi to pi at the end. That would be minus pi to pi when we're talking about eta j omega. This would be, minus omega sub s over 2 to omega sub s over 2. But I showed you that there's a relationship between omega sub s and actually the small omega. Okay? So look at this. You see this? You see this part aliasing in? That will be the Fourier transform of my discrete time signal. Okay? The DTFT of my discrete time signal would look like this. And it's real. Here's an example. See this? This is a cross-section of a head, an MRI cross-section of a head. In MRI, we sample in the frequency domain. Okay? So we need to compute a Fourier transform to get to this. This is exactly what happens. If you didn't sample enough in MRI, in the frequency domain, you get aliasing or replicas of your signal. Okay? There's always this analogy. I mean, what is frequency and what is time? You can always reverse them by Fourier transform. An inverse Fourier transform and a forward Fourier transform are related to each other. So it doesn't really matter which domain are you sampling if you think about what aliasing is. So if I sample in the frequency domain, and I don't sample enough, I'm going to get aliasing. And so the back of my head is going to alias to my nose. Happens all the time, sometimes on purpose. Because some people's noses are too big. They need more field of view, but then it only overlaps with part that is actually the back of the neck. It's not the brain, and we're interested in the brain sometimes. So it doesn't matter. So you can do tighter sampling. Sparser sampling. So less measurements, skip more samples, then get some aliasing, but it's not aliasing that's important. In this case, somebody decided to use an anti-aliasing filter. So you don't get that overlap. Okay? Now here's the reason. If I sample in this domain, if I sample according to the Nyquist criteria, that basically that sampling that is twice at least, so if delta k is at least 1 over the field of view, which would be the bandwidth, if you think of the analogy. If one domain, a bandwidth is how much, what's the band of frequencies, in the other domain is how much field of view. Okay? So if I sample fine enough, I will be able to reconstruct. If I now don't sample fine enough, I will get aliasing or replicas. This is in more dimensions, but it shows, again, the same phenomena. Here's actually a cool one. This is a cross-section of an abdomen of a pediatric patient. Okay. This is part of the liver here. This is the spine. This is part of the liver, and you see this stuff that's going through. This is not a blood vessel. It's kind of weird why it's even inside the object. As it turns out, this kid has an IV tube. And the tech put the IV tube pretty far away from the body, so it increased the field of view. But they designed the scan to measure that field of view, so whatever here, aliased over. So if you redo the scan with the right sampling, you see the IV tube over here. And that IV tube actually aliased inside the body. So techs should always put the IV as close as possible. Also, often people are scanned that way because that increases your field of view, so you need more sampling. Or you do something like this. All right. So now we have samples. We know in order to avoid this overlap, we need to sample at a particular rate, right? That is at least corresponding to the bandwidth of the signal. Okay? Twice the highest frequency, which is really what's the bandwidth. Okay? From negative to positive frequencies, it's twice the highest frequency. So here's the beautiful Nyquist theorem for band-limited signals. Okay? So it says the following. Suppose x sub c is band-limited. So it's non-zero only between the frequency minus omega n to omega n. And it's zero elsewhere. Okay? So it doesn't have any high frequencies. If that is true, and you sample at a rate of twice the sampling frequency, then, and that's amazing if you think about that, x sub c can be uniquely determined from its samples. So if you actually made samples of it, discrete number of samples, you know everything that needs to be known about this continuous time signal. Everything. It's crazy. Right? Everything. I have discrete samples and I know everything about the continuous time. That's insane. The reason is, though, is the band limitedness. Okay? That's really the key. Okay? Because if I have samples of this band limited signals, okay, and I want to reconstruct. What does it mean? I want to interpolate between those points and say, what is the value here and 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 all those places? Okay? If I tell you that the signal is band limited, that gives you a unique signal that can be interpolated from here to here. That's band limited. There could be other solutions though, right? That's a good one, right? That's a good one. That fits, right? I have samples. Yeah, if I sample that signal, I will get exactly the same measurements. Exactly the same measurements. Hey, so what are you talking about? Like you said that it's uniquely reconstructible, right? But now you're showing me, Mickey, that there's more than one signal. You know what? There's even another one. That one too, if I sampled it at those points, will give me the exact same thing. How can you say that you can reconstruct? Well, the reason is that these are not band limited. Okay? They have a higher bandwidth. So yeah, they're going to alias, but I will never be able to reconstruct this from those measurements based on the band limited property. Okay? If I'm telling you it's band limited, then that is the only one that will go through. Okay? Does this make sense? And that's what we're going to do right now. We're going to try to look at the reconstruction in the frequency domain and understand actually what is going on. Okay? So the reconstruction will take X of... Any questions? Any questions? This is a serious moment. It's a serious moment here. It's actually a really strong assumption to tell a signal, hey, dude, you're band limited. Right? You're really restricting it. And that what allows you to sample it. Because it is restricted. Okay? That also allows us to reconstruct it. And so what we're going to do is we're going to take X of n. We're going to convert it back. Here's the reconstruction. Convert it back to an impulse train. Now it's continuous but impulsive. Okay? So this is an amazing device. I'm not sure how to implement it, but it's an amazing device. It makes it into an impulse train with the right amplitude at times t. So now I've got back X of S of t, the one that I love. Because it's continuous time, I can do a continuous Fourier transform. It's beautiful. Then I'm going to filter it to get the reconstructed signal. I'm going to filter it in the analog domain. Okay? To do that. So if I look at the Fourier transform of X sub S of j omega, it's going to look like this, right? Remember that omega sub S over 2, that's exactly was the pi for the DTFT of X of n. Right? It is periodic, right? That's why they relate to each other. Now, if I know it's band limited with that particular bandwidth, okay, a bandwidth which is twice the highest frequency, which is omega sub S over 2, if I know, in order to reconstruct in the signal, all I need to do is take out the high frequency and leave the low one. It is band limited. That's our knowledge. Otherwise, there's many signals that I can go through filtering that would result in the same samples. Okay? But here is just one. So what I'm going to do is I'm going to filter it with a low-pass filter. And I'm going to end up with a reconstructed signal. Note the capital T here, the gain, to compensate for the loss of gain when I multiply by the impulse. Okay? So now I've got back what I've started with. That's the Fourier transform. In the time domain, what do you do? It's A. So here's a multiplication with a filter, an ideal low-pass filter. What would be in the time domain? A circular convolution? Not a circular convolution. A convolution in continuous time with the inverse Fourier transform of this ideal low-pass filter. So if I compute the inverse Fourier transform of this ideal low-pass filter, very easily from a rect function, you would get to a sinc function that is scaled with t. Okay. So my reconstruction is the following. Convert into an impulse function, and then convolve with a sinc function. Okay? That's it. Simple. Beautiful. Here's how it looks. Convert to an impulse function, convolve with this impulse function. If you convolve convolve with a low-pass filter, a reconstruction filter. This is an impulse train. When you convolve with an impulse train, you're going to get replicas on top of each of those impulses. Okay? Like we got from aliasing, right? It was exactly the same thing. So now, the result will be a sum of the coefficients of those delta trains, which are in fact x of n, scaling these sinc functions and shifted. So the result is just scaled shifted versions of a sinc. So if I have this, and I know it's band limited, what I'm going to do is I'm going to take a sticker, a sinc sticker, it's a band limited sticker, and I'm going to stick a sinc to each one of those points. Okay? Now it's continuous time. One sticker, second sticker, third sticker, fourth sticker. Look at the beauty, by the way, that when you have a value over here, it's always 0 when the other samples occur. But it's not 0 in between. Oh, 0. Oh, 0. 0. Exactly when the samples. That's the beauty of that sinc. And so I'm just going to put all these stickers and now sum them together to get the continuous time signal. Ta-da! And how do I know it's band limited? Because it's the sum of sincs. The Fourier transform of a sinc is band limited. There's no nonlinear operation that would give me high frequencies, so they are limited by the bandwidth of that sinc. Hence, band limited. Huh? It's pretty. Okay? So the fact that I summed these sincs gives me this unique reconstruction. Okay? If I would sum triangles, by the way, that would be like a linear interpolation. Right? Triangular functions. That would be a linear interpolation. When you do a linear interpolation, understand that you're not having a band-limited signal because the Fourier transform of a triangle, is not actually going to is not going to be band-limited. Okay? It is actually sinc square in the other domain. So it is going to be, has high frequencies. Okay? It could be a good approximation. Okay. So now what's aliasing is, right? If omega n is bigger than omega sub s over 2, then you're going to get x of r will be an alias version of x of c. So I sampled and I reconstructed. If I reconstruct something that was not sampled at the Nyquist rate, what I'm going to get is an alias version. Okay? Now, in order to really solve this issue, that now I kind of screwed up part of my spectrum that I might have been interested in, what could I do? Right now, there's nothing I could do. It's already done. Once you sample, You get aliasing, you lost. Okay? What could I do then? Do something against it. Anti. Aliasing? No. Anti-aliasing. So what do? I take, my signal is really not band limited, or not band limited to the point where I'm going to sample it. Okay? I cannot sample as fast as that signal requires. It has more frequencies. But I still want to get, a good signal, like something within those frequencies that I'm interested in at least. So what I'm going to do is I'm going to make it band limited. I'm going to make it band limited by filtering it before I sample. After the analog anti-aliasing, now it is band limited. Now I sample and quantize. Okay? So if ecstasy would alias to this, if I'm going to filter it beforehand by an ideal analog filter, right? With an ideal analog filter, then now I'm not going to get aliasing. I'm going to filter out those high frequencies. I won't be able to see them, but at least they're not going to alias in and ruin my entire signal. Okay? So before you doing any operation of sampling, it is often required, I would say advised and even required, to do a low-pass filtering anti-aliasing before. Okay? Sometimes you don't want to do that. But there is a reason, other reasons for this. Okay? But often you want to do this, otherwise you're going to basically get aliasing on top of your signal. So now here's a question though. I said that you need to do an ideal filter. But what if it's not ideal? What do you do? Well, you have to do something. So what can you do? Come on, engineers. Yep. Windowing where? What should I do? Come on, it's practical. We do it all the time. You lose a low-pass filter, right? That kind of diminishes, right? Then what do you do? Well, I mean, it still has signals over here, so what's going to happen then? You might actually sample at a little bit higher rate. That's right. That's right. You're still going to get some aliasing, but the aliasing would be really low. Yes, exactly. Or you can steal some of that, right? And still, start filling it here and screw up some of your signal. Then you can maybe correct it visually afterwards. Maybe. Okay. So here's something about non-ideal, right? And this is often the case. This is a case that happens all the time. You actually are filtering something that looks like this, okay, instead of an ideal filter. What if you have also like an interference over here? What would happen then? When you have that, then when you sample, you get, tiny bit of aliasing because only that part aliases, but it's already quite attenuated. Okay. So it does alias a little bit. What about this big one? Right? That never happens, huh? Right? So just to demonstrate it never happens, I brought a signal generator and an SDR. I'm going to generate frequency that's outside of the band that I'm going to sample. And we'll see what happens. So, yeah, how about 144, 432? How about that one? 144, 432. Well, there's a lot of interference here. Let's move to a different frequency. How about 1144? Okay. So it's another one here. 1144, 234. And I need to turn it on. Oh, there you go. See it? 144, 432. Okay, so this is the 432, 144, something 432, right? That's the one. Okay. Now, the maximum frequency supported by this sampling is 144, 5 something. Okay. And basically, the way it works, you have a low-pass filter, and then you whatever exactly. I'm going to start moving it. So I added 10 kilohertz and a 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 10 kilohertz, 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 10, 10, 10, 10, 10. By the way, you see these ghosts that kind of behave the same way. That's because the gain is pretty high and there's some nonlinearity. But I'm going to reduce the gain, so now they don't exist. But now the signal doesn't exist. Okay, so all right, now it works. Okay, so now I'm getting out of the spectrum. Look at this. I'm getting out of the spectrum. Ready? Oh, more. What's going to happen when I get out of the spectrum? Ooh. Hello. But. Thank you. Exactly this. Okay. By the way, from this you can actually measure what is the amplitude response of this anti-aliasing filter of this particular device. Just by shifting those frequencies and sweeping them, you can actually characterize it pretty well. Okay, you can actually measure this. All right, questions? Yes? How do you create an analog anti-aliasing filter? Capacitors, inductors, series parallel. You have a network of capacitors and inductors. That's one way. There's also MEMS devices, SAW filters that SAW is surface acoustic wave filters that couples electric properties and mechanical properties inside a semiconductor device to create filters.
So are you able to create that sharp transition like that in that filter?
This sharp transition? This one? Yeah, it depends on the order of the filter, how big it's going to be, how expensive, how much capacitance you're going to have there. So there's all issues for analog IC design. Okay, if you want to make that into IC, sometimes you make it out of discrete components. So you can buy this, big filters, big inductors, big capacitors, and so on and so forth. Okay. You can also change, the filters as well by changing, doing variable capacitance by, let's say, changing the gate capacitance of a transistor, right? By putting different biases on it, so you can actually modify in an analog IC circuit, the properties of a filter. And this is actually how this thing is actually working. Okay, because it's really a small chip, all the filtering is done in it. It's quite amazing that it actually works at all. That wasn't me, but I think it's time to go. So have a nice weekend, and I hope you enjoyed the lab. Watch a lot of airplanes.